Another strange consequence of the weird representation of arrays in C, that strange quasi-pointer thing, is that it isn't possible to return an array from a function. And I have a good justification for that, but we're not ready for it yet. We need one more week. So bear with me. You can try it. You'll discover it isn't possible. But in the meantime, I'll prove my point once and for all next week. But what we have to do is find some way to live with that. What if a function produces an array? In the previous video, we wrote some functions that work with arrays, or that in the case of the reverse function, it took an array and modified it. What if the job of a function is to create an array? Well, that's a tough one. We're used to, if we want the function to create something, we pass in arguments, the function creates a number and then returns it. But I just said we can't return arrays. And it actually isn't because arrays can't be a return type, although making them a return type is surprisingly challenging. It's because of the way that the array gets allocated. And to give a sort of brief idea of this, suppose we have a function here. And the function contains some array, and so it looks like this. There's my array, okay. And then the function tries to return the value of a. Well, the problem is the value of a is an arrow that points at this thing, and that's it. So the return value would be this arrow. But then the function ends and the scope gets destroyed. And so now whoever called the function f has a pointer that points at nothing, which is, of course, very unsettling. And that's one of the reasons, that in short is really why we can't return arrays. But there's some technical complexity behind that we can't describe just yet. So we can't return an array, but then what if the function's job is creating an array? And the solution is, what we have to do if we want the function to create us an array is we have to make the array ourselves before calling the function, and then pass it in, and the function then fills the array up with data. So down here in main, I create two arrays, a and b, and then I call this function. Notice that before I call the function, the arrays a and b aren't initialized. So I call this function, and the idea is the function takes my array and it fills it up with data. And then when the function is finished, I can print the array out. And that is the standard protocol when you work with arrays in C. You pass the array into the function then deals with the array, and then when it's done, the data that was supposed to be there has been left behind in the array that you passed in. So the caller has to provide the storage. This is something that's pretty unique to C. Other languages do have, the Java and C++ and Python all have features that make it pretty easy to just create and then return an array from a function. There's no need to create the array outside like we do in C. So you'll notice on assignment 4 is full of functions like this. Here's an array, produce some result. Use this as storage for some result. So this function is designed to look a lot like one of the functions on assignment 4. And because I'm just proving a small point, I didn't even write out the full. I should have done this. It is on the assignment I do this. I didn't even write out that full return value and parameter specification. So the idea is, if I hand you an array, let's give an example here. So I hand you an array of size 4. And I give you a starting value of 7. Your job is to fill in the array with the values 7, 8, 9, 10. So you start counting at the value I provide, the value v, and you set every element in the array, starting at element 0, to be v, then v plus 1, then v plus 2, all the way up until the end of the array. So hopefully the problem isn't conceptually that difficult. All right, so notice that what I'm really doing here is I'm setting the first element to be v plus 0. And it looks a lot to me like what I should do is just, for each index I would set the value of a at index I would be v plus I. So what I need is relatively straightforward. For int I equals 0, I is less than n, I plus plus. There's that loop again. I would write a sub I equals v plus I. Oh, not plus 1, plus I. There it is. Okay, so this is enough, hopefully, to fill up the array as required. It only, well, not n. Okay, I need to be more careful here. I've changed notation styles between examples. So I is less than size. The value here is called size. And then I just walk through it one at a time. Okay, so we'll try compiling this, and it's complaining about n. Yeah, I get it. I tried changing it already. Damn it. Okay, there we go. And we try running it. And I just want to describe these results. So here we are in main. And the first thing I do is I call counting array. I give it a starting value of 6, and I give it an array of size 5. So we should get 6, 7, 8, 9, 10. And we do. And then I call it on my array B. I start counting at 10, and so I should get 10, 11, 12, 13, 14. But then there's this question. So when I call the function, I give you a starting value, and then I give you the size of an array and the array. Okay, so here's I've got this array in main called B. And B has size 5, so it's an int array. It's got size 5, okay, and there are its elements. All right, and I hand you B, and I tell you the size of B is 5, and you believe me, and you go set the elements of the array. What would happen if I told you that the size of B was 3? Would you still be able to do the job? I mean, really, 10, 11, 12, well, yeah. If I tell you the size of the array, but I lie to you, well, that's my problem, not yours. You can still do your job. You just use whatever size I give. And it turns out that that's actually a valid thing to do. It's perfectly valid to tell the function that the size of the array is a size other than its real size. The important thing, though, is to make sure that you never overstate the size. If B has size 100, it's completely valid to tell the function that B has size 5, because B definitely has enough space to store 5 things if it actually has size 100. It would be a very grave error to tell this function that B had size 7. Because if you told it that B had size 7, then the function would say, okay, I believe you. Okay, we'll set this index to 13, 14, 15, 16. And that's what it would just keep walking. It would walk right off the end of the array into strange unknown space. Well, we'll talk about that part next week. That's spooky enough that we have to have that closer to Halloween. Okay, so there's that issue, but it is perfectly valid to say that when we talk about arrays, to say that to hand an array over to a function and then understate the size. But it's also really important that we understand the implications of that. So down here at the end of main, I try that out. So I call counting array, and I say start counting at 10, just like before. But I'm going to give you A, the array I already used. At this point, as of line number 42, A contains the values 6, 7, 8, 9, 10. And I hand it back to the function, and I say A only has size 3. And the function runs. And then I print out all of A. But because I told the function that A only had size 3, then naturally the function isn't going to step on these last 2 elements because it doesn't know they exist. The function thinks this is the only game in town. This is all of A. But it's valid to do this. You may notice the compiler didn't give me a warning. And if I scroll down and take a look, there are the contents of A. The function accepted A and treated it like an array of size 3 because it's an array of size 5. An array of size 5 can always sub in for an array of size 3. I guess as an experiment, what happens if I tell this thing that the array actually contains, 100 elements? If I tell the function to keep walking for 100 steps, even though the array itself actually already ended after 5 elements. And the answer is undefined behavior. So I'm held in suspense just as much as you are right now. Ooh, okay, this is fantastic. Okay, so I call counting array, and then I print out A, and then I print out B, and that looks good. Then I print out A again. So I make it all the way to this point. And you notice A does contain 10, 11, 12, 13, 14. And then I get this incredibly ominous error, stack smashing detected, and then unknown term. So you can see clearly I've upset the operating system here. And what's happened is I've walked past the end of the array into unknown space. I've left the area of memory that has been assigned for my own data, and I've wandered into the neighbor's yard. That's something we're going to talk about next week. You don't worry. I really want to meditate on the subject of what happens if we walk into the neighbor's yard.